When heteroatoms are part of the ring, heteroatoms being any atom that is not carbon or hydrogen, we could also have the ring still being aromatic, non-aromatic, or anti-aromatic. And the first thing that we should do before we ask any of the questions is to draw in any lone pairs that aren't shown. And so on the nitrogen at the top, we have lone pairs, and also on the nitrogen at the bottom right of the ring, we have lone pairs that aren't showing. So now we've at least drawn everything that we're really going to need for counting our pi electrons and for seeing if the atoms are, what hybridization they are. And so that's the first thing we're going to ask is, do all the atoms in the ring have p orbitals? In other words, a lot of the times this translates to, are they all sp2 hybridized? And we do see those carbons that are involved in double bonds, so we can say, well, those ones are all sp2 hybridized. But then when we take a look at the nitrogens, we also have to decide. So this nitrogen here is attached to a lone pair, a carbon, and another carbon. And this lone pair can't move anywhere, so it can't do resonance because we already have the nitrogen using its p orbital in this double bond. And so if we're thinking about how many things attached to this nitrogen, we have 1, 2, 3. That lone pair isn't going anywhere, so this is also going to be sp2 hybridized. And we'll draw out the orbitals in the next slide too to figure out where everything is. So for the first one, for the top one, if we initially look at it, it looks like we have a hydrogen, a carbon, and a lone pair. So it looks like it might be sp3 hybridized, but if we think about whether this lone pair can do resonance, it is next to a pi bond, so we could do resonance with that lone pair. So we could bring this lone pair down, this bond out onto the nitrogen, or we could have gone the opposite way if we wanted to. And that's going to mean that since that lone pair can participate in resonance, it's going to be in a p orbital, and also it's basically not going to count for that count in terms of how many things are attached to that nitrogen. So if we draw that resonance structure out, and then we're taking a look at this resonance structure that we drew, we're going to have 3 atoms only attached. That lone pair no longer is actually belonging to that nitrogen, and so this looks like it's sp2 in this structure. Another way to think of it is that we did use that lone pair in resonance, so we don't count it as a thing. So in this structure, the H and the 2 C's will count. So we're going to have all of our atoms being sp2 hybridized, so we can say yes, that they all have p orbitals. When it comes to how many pi electrons can circulate in the ring, we're thinking about those double bonds, so those pi bonds. We're also thinking about lone pairs. Not all lone pairs are going to be able to be counted in this. And what we can see from our molecule is, like, definitely there's going to be 4 pi electrons at least, because we do have these 2 pi bonds. We have also this lone pair up here that we drew in resonance to figure out what the hybridization of this nitrogen was. And since we're using it in resonance like that, it does have to sit in a p orbital. And so these are going to count towards the total as well. So far we're at 6, 2 from here, 2 from here, and then these 2. Now we have to figure out, what about these ones? Because these 2 electrons we didn't draw. We said they actually couldn't resonate. And the reason that we're actually not going to count these electrons is the fact that they're actually not in a p orbital. We're going to draw, what type of orbital are they in the next slide, but they're actually not in a p orbital. A reason for this is that the nitrogen is using its p orbital to overlap and make the bond to this carbon, and so that p orbital is already being used. These lone pairs are not sitting in a p orbital. We can't move those, so they're kind of fixed on that nitrogen. Because they're not sitting in a p orbital, we don't count them for pi electrons, so our total is going to only be 6 pi electrons for this molecule. So we can go 4n plus 2 equals 6. When we solve for n, we're going to get 1. And then we ask, is the ring flat? We see that it's a 5-membered ring, and we've already said that all of those atoms are sp2 hybridized, and so yeah, the ring has to be flat. So all of these all the rules end up being satisfied, so this molecule is aromatic. Let's take a look at a little bit deeper in terms of where are those pi electrons. How come we didn't count the 1 lone pair on the nitrogen? And this is a diagram of all of the orbitals that we have for the pi system, and then one of the sp2 orbitals is actually drawn out. So basically what's going on when we have these pi bonds, this is made from overlapping p orbitals. So these purple ones here, these two and these two are overlapping to make this bond and this bond respectively. And then we also have the lone pair that we showed in resonance. So we showed it with arrows going down and this coming out. Really what's happening is that these lone pairs are just sitting in a p orbital, and they're actually able to overlap with all the other p orbitals because they're all in the same plane. That is kind of what we draw the resonance hybrid for usually for a molecule is kind of getting the closest to this type of structure without drawing out the orbitals each time. But what's happening with that lone pair on that nitrogen, since we were saying that it was resonating, we show that with our arrows. That means it's in a p orbital, which means it's overlapping with all the other purple p orbitals. So those are all the pi electrons. We said two in this bond, so there's two electrons and this, and Alex, so kind of one here, if you want to think of it that way, one in this orbital, one in this orbital, if you want to think about it that way, overlapping to make the bond, and then two electrons on the nitrogen. So that's where all the pi electrons are coming from. The nitrogen's other bonds, so we said that the two nitrogens are sp2 hybridized. We actually said the other ones are too, so they're doing the same type of thing. But with the nitrogens, what's happening, so this nitrogen has a p orbital, but the other three orbitals that it's using to make the bonds to the three atoms, the carbon, carbon, and the hydrogen, the orbitals it's using are sp2. So this sp2 orbital is overlapping with the hydrogen's s orbital. This sp2 orbital is overlapping with this carbon's sp2 orbital to make this sigma bond. And then this nitrogen, or the nitrogen's sp2 orbital on this side is overlapping with this carbon's sp2 orbital to make this bond. So that's why these are mentioned as sp2, because it's using its sp2 orbitals for those three, and then its p orbital has the lone pair. For the nitrogen down here, its p orbital is actually involved in the pi bond, and so the other three orbitals are still all the sp2 orbitals, because with sp2 hybridization, you get three sp2 orbitals and one leftover p orbital. We already are using the p orbital in that pi bond, and so the other three are going to be sp2 orbitals. So one of the nitrogen's sp2 orbitals making the bond to this carbon by overlapping with that one's sp2 orbital, and then the same thing's happening up here. The other sp2 orbital is what actually contains this lone pair here. And so the sp2 orbitals, if we think about how everything comes together, sp2 orbitals are 90 degrees away from the p orbitals around the nucleus of the atom, and so they actually can't overlap, and that means that like this sp2 orbital is actually 90 degrees. There's no way it can overlap with this, and that's kind of why we don't show the resonance, because we can't have the overlap when they're not in the same plane. And so with that nitrogen, we don't have the resonance because it's in an sp2 orbital. For that lone pair as an sp2 orbital, so we don't have that resonance, and we also therefore do not count it for our pi electrons because it's not in a p orbital.